Alright guys, here's our fourth video, continuing where we left off from. So we were talking a little bit about what is a hypothesis. And a hypothesis is something that we can test. We can test to find out whether echinacea reduces the duration and symptoms of a cold. So our hypothesis would be echinacea reduces the duration and severity of the symptoms of the common cold. So then, in order to test that hypothesis, we can conduct a critical experiment. So in this case, we have experimental group. Researchers randomly divided 437 volunteers into 4 groups to test the effect of echinacea on the common cold. So then in each one of the groups, in the first group, they take 1 placebo tablet daily, a placebo being a pill, like a sugar pill that doesn't have any of the medicine in it, but the group doesn't know whether they're getting the echinacea or they're getting a placebo pill. And then we have the group number 2 that takes 1 echinacea tablet daily. And groups number 3 and 4, they have no treatment, in order to determine if treatment prior to exposure has any effect on the development or duration of the symptoms. So groups 1 and 2 receive tablets for 7 days longer than groups 3 and 4 in order to determine if treatment prior to exposure has any effect. So here we look down here and we see all of our cold-causing viruses. And so, thinking about what the role of experiments are here, it's important that we try to demonstrate that our initial hypothesis is not supported by the data. And if it's not, we might adjust our hypothesis. We make revisions, we change things about the hypothesis and make it so that it's specific and make it so that it's testable. We have to be able to test something in order to find out whether it's supported or unsupported. So does echinacea help prevent the common cold? We see all of our treatments here and then our conclusions. If individuals from all 4 groups are unequally likely to develop a cold, cold symptoms lasted for the same amount of time, echinacea had no effect on the duration or severity of the cold. So after further experimentation, after we come to our initial set of conclusions, we can change things and further experiment. So we can experiment with the amount of echinacea that's given. We can alter the length of time that the subjects receive the echinacea treatment. So echinacea reduces the duration and severity of the symptoms of the common cold. We have found that that is unsupported. So at what point have we tested our hypotheses so many times that they actually become theories? Theories in science doesn't mean a guess. Like if you hear somebody on CSI say, I have a theory that that this is going to have this effect. A theory in everyday common language usually means a guess. But in science, theory is something that means we have a level of understanding that is supported by so much evidence that has been tested so many times that theories have been found to not have any evidence against them. So a hypothesis is this proposed explanation for a phenomenon. A good hypothesis leads to a testable prediction. And then finally, when we get to a theory is a hypothesis for a natural phenomenon that is exceptionally well supported by the data. It has withstood the test of time and it's unlikely to be altered by any new evidence. So when we talk in science about things like cell theory says that all living things are made up of cells. We have never found one living thing that was not made up of cells. So therefore, that theory is exceptionally well supported. We've found so much evidence that everything that is alive has cells inside of it that nobody says, oh, there's lots of things that are alive that don't have cells. So The difference between a theory and a hypothesis is that a theory is repeatedly tested and it is much broader in scope. So in talking a little bit about the experiments, experiments in order, excuse me, I yawned. In order to be a good experiment, it needs to have a treatment, which means any kind of experimental condition applied to the individuals. We have an experimental group, which is individuals who are exposed to a particular treatment. We have a control group, which is one that goes through the experiment, but they are not exposed to the treatment. And then we have our variables, which are characteristics of our experimental system that are subject to change. And so, in a good scientific experiment, we can control these variables. You may have heard of independent variables or dependent variables, and these variables are the most important feature of a good experiment. They attempt to minimize any difference between a control group and an experimental group other than the treatment itself. So sometimes when we are doing these experiments, we use what's called a placebo. You may have heard of the sugar pill, or a pill that doesn't have any effect. And so the placebo effect is when a person responds favorably to a treatment that doesn't actually have any of the actual drug or actual treatment inside of it. And so the placebo effect highlights the needs for comparison groups. If we don't look at what happens to people who think they're getting the treatment, or who don't know that they're getting the treatment, that can be a big factor in an experiment. This is an interesting story about a horse that can do math. It used to be back, earlier in the 20th century, that this gentleman thought that he had a horse that could do math. So if you say to Clever Hans, what is 2 plus 2? Clever Hans would start tapping his foot on the ground, and he would tap once, twice, 3 times, 4 times, and so 2 plus 2 is 4, and then he would stop tapping. And so they did all kinds of math problems with this horse, and what they found is that whenever they would ask the horse a question, that his owner would be right there next to him, that they found that eventually his owner was giving him cues as to the right answer. And so if the owner of the horse didn't know the answer, then the horse didn't get it correct. But as long as his owner knew what the answer was, the horse would be able to get it correct. And so even though the horse didn't really know math, the horse could read his owner's body language or cues and know when to stop tapping. And everybody thought it was because the horse knew math. It was really that the owner was giving cues to the horse. So in an experiment, we can come up with some experimental designs that help us to be able to tell whether the experiment is really testing what we're thinking it's testing or not. In a blind experimental design, the environmental subjects do not know which treatment, if any, they are receiving. So if we're doing drug trials, the subjects don't know whether they're getting the sugar pill, which is the placebo, or the real treatment. And in a double-blind experimental design, this means that neither the experimental subjects nor the researcher knows what the treatment is. Because sometimes if the researcher knows that the person is getting a sugar pill, they may treat the experimental subjects differently than if they didn't know who was getting the experimental treatment and who was not. So the hallmarks of an extremely well-designed experiment is that they use blind or double-blind strategies, that they randomly assign people or experiments or people or groups into experimental groups or control groups. So we want to see in a good type of study these strategies being used. So one thing about experiments that we've found is that they need to be repeatable in order to increase our confidence. If we only have an experiment that's done one time, then how do we know that we didn't taint the sample or have some kind of contamination? Science can be misleading when we only do an experiment one time. So we've got to watch out for things. In science, biases are the researcher expecting to see something. Sometimes science, since it's been done by old white men, can be somewhat sexist or somewhat racist. So how would we know? We have to watch out for those things, and we have to expose those things. So one of the things that's interesting about science is that they did a study where papers published by female scientists, if the reviewer of the journal knew the sex of the author, then 23.7% of the time they would publish a female first author. But if they did not know the sex of the author, then they tend to get females published a lot more often. So because that is, because we are seeing differences between when they know and when they don't know, we know that there is some kind of bias there. So scientific thinking can help us to make wise decisions. Here you see a picture of someone who is reading food labels. And that is definitely something that you should do as you're trying to figure out, how am I going to be healthy? Looking at variables, independent variable versus dependent variable. In an experiment, we have things that we can measure and things that we can change. So an independent variable is some type of measurable identity that is available at the start of the process and whose value can be changed as required. So independent means that it can be changed, and dependent means that it's created by the process observed and whose value cannot be controlled. So dependent is the thing that is measured. And so that brings us to the end of what we're going to talk about for Chapter 1. On Tuesday, we will meet again in Schrank South 145, and we'll be able to talk a little bit more about this. The next step, the next thing that you should be doing is submitting this set of notes, doing that through the Dropbox, and the instructions are on there. And so